All right, so lesson 5 is Lewis electron dot symbols and bonding. Okay. Lewis electron dot structures for neutral atoms, and then we'll talk about them for ions. Neutral atoms, the only thing you're going to have to know is the number of valence electrons, and then you're going to draw one dot to represent each of the valence electrons for that particular element. For example, sodium is in group 1. Every group 1 element has one valence electron. Therefore, sodium is going to have one dot like so, representing just the valence, not total electrons, just the valence. Sorry, I meant for example, we can see the electron dot structure there, but we can also relate that to what it would look like if I were to just write out the configuration 281. That indicates that there's 2 electrons in my first orbital, our energy level. There's 8 electrons in my second energy level, and then there's 1 in the outer energy level, which is the valence. And so I represent that one dot. Ions are represented a little bit differently. We still, of course, indicate the dots, but we also have to show the charge of the ion once it's formed. For positive ions, it doesn't have any dots. That's the whole purpose. Sodium loses that one valence electron, so there's no dots. So we just write the symbol and the charge. So, for example, if I were to write the electron configuration for an ion of sodium, it would be 2,8. It would have the same configuration as neon, the noble gas closest to it. Now it has that 8 valence electrons, that octet, which makes it stable, and so it's charged positively, Na+. Negative ions, we do have to show the dots. In general, and this is not like a hard, fast rule, but it is the way that this book and these resources write most of theirs, so we're going to just go with it. We put our dots representing that octet of electrons that have formed now that we've gained. And then we place that in brackets. Outside of the bracket, then you indicate the charge of the anion, like phosphide or phosphorus, a phosphide ion. Also has a stable configuration like a noble gas, 288. It's like argon. That's what the noble gas it resembles. And it has its 8 valence electrons, but in order to get there, it had to gain 3 electrons. So its charge is now 3 negative. We can show ionic compounds and how they form and what their final form, where the electrons have gone, how they were transferred by using electron dot structures. In order to do it correctly, though, we have to have the correct symbol and charge of the positive ion. You have to have the correct symbol and charge of the negative ion. So that's what we just did on that side. And then, of course, the correct number. You have realizing that the charges have to be balanced. If one of my ions is a +1 and my other one is a -3, well, I have to have 3 positives to balance that out. Oh, yeah, that's next. Mm-mm. So, for example, if we wanted to show the completed ionic bond between sodium and chlorine, using electron dot structure, it would look like this. We show our sodium ion, which is Na+, and then chlorine will have its octet, and it's negatively charged. It gains 1 electron when it becomes an ion and achieves stability. And I'll show you calcium bromide and potassium oxide. Come on. All right, so if we have calcium, calcium, if we were to look at the neutral atom of calcium, it's in group 2. It has 2 valence electrons. So it's going to lose those valence electrons and become 2 positive. Bromide is the bromine ion. So bromine is found in group 17. So neutral bromine has 7 valence electrons, like so. Because, though, this bromine is going to be a negatively charged ion, because calcium is going to donate one of its electrons. But this is not going to balance my charge out. I have 2 positives, and right now I only have 1 negative. So in order to balance this correctly, I have to indicate that there's not just 1 bromine, that there are 2. And you can do that pretty simply by putting a coefficient there. This indicates I have 2 positive charges, and now I have 2 negative charges. It's electrically neutral when bonded. The other one, I don't remember what it was. Potassium oxide. So I have potassium. Potassium is a group 1 element, so it is going to form a positive 1 ion. And then I have oxygen, which neutral oxygen has 6 valence electrons. So a stable oxygen would have to gain 2 electrons and be negative 2. Obviously, it's going, these electrically, it's not balanced here. I have 2 negatives and only 1 positive. So I'm going to have 2 positive potassiums. So that's 2 positives and a negative. And now I have my formula. Questions about that? All right. Molecular substances are going to take a bit more, I don't know, I think they're a little bit more challenging. Only because when we're doing molecular substances, there's we have to know which bonds are shared, or which ones are electrons are shared, and which ones are what we refer to as lone pairs. For a correctly written Lewis dot structure for a molecular formula, a covalently bonded compound, you have to have the correct symbol and the number of each nonmetal ion or atom. There's no ions present. Correct number of shared or the bonding electrons between the atoms, and the correct number of valence electrons. 8 is still the goal. So, but instead of achieving 8 through losing and gaining those electrons, we're simply going to share them. Those shared electrons then create covalent bonds. Some examples of covalent bonds represented with electron dot. The first one there is hydrochloric acid or hydrogen chloride. You can see that there is a line connecting hydrogen and chlorine. That represents 2 electrons. So in this case right here, we have 2. It's important to note that if we were going to look at hydrogen, it is an exception to the octet rule. Hydrogen is stable when it achieves 2 electrons because it will be like the noble gas helium. Okay, so this line represents 2 electrons. So hydrogen has 2. And then if I go and look at my other atom, I want to make sure it has 8. There's 2, 4, 6, and then this shared pair means 8. So hydrogen is stable, chlorine is stable. Here I look at a water molecule. Again, hydrogen, all you can have is 1 bond to hydrogen. There's never going to be double bonds, never going to be triple bonds, and there's never going to be lone pairs. They're not going to be sitting outside of that because 2 is the magic number for hydrogen. So this line right here represents that each of these hydrogens are fulfilled by sharing electrons. And then oxygen then has a pair here, and then these 2 bonded. So 2, 4, 6, 8. Oxygen is happy. Next, we have ammonia. Ammonia is NH3. Again, my hydrogens are all nicely pleased here because each of these hydrogens have 2 electrons. And if I count around my nitrogen, there's 2, 4, 6, 8. So we do not show, there's no ions, there's no transfer, there's no charges. We just have to make sure we show how the elements are connected to each other. Yes. The last what? I don't know. Hang on. Non-polar substances. Again, remember we talked about symmetry and asymmetry and how that affects polarity and non-polarity. The ones that we just saw on the last page are asymmetrical. These are all symmetrical. Non-polar substances here have, and we can still do the same count. Every non-metal wants to have 8 electrons. So I look at carbon in the middle. There's 2, 4, 6, 8. And then I look at each of the chlorines. Each of these chlorines also have 8 electrons. Chlorine bonded to itself. So I represent the shared pair. They're sharing a pair. 2, 4, 6, 8. And then this one has 2, 4, 6, 8. Yes, the line always means 2. In this one down here, carbon dioxide, there are 2 lines. Each of those lines represents 2 electrons. So this is actually a total of 2, 4, 6, 8. So carbon has 2 different shared pairs on each side. And then oxygen has its 2 lone electrons, or 2 pairs of lone electrons on the outside. But this is a double bond. Double bonds are stronger than single bonds. Triple bonds are stronger than those. And then methane, which is like so. Each of the hydrogens still have 2 electrons, and then the carbon has 8. That's it. We're going to practice our bond writing and molecule writing.